now that we've done the change of base formula, and we know that the log base, any b that we want of a number, is log base 10 of that number over log base 10 of that base, or even in that quiz, we found out we could do it with a natural log. We could take the natural log of the number over the natural log of the base. We now know we can evaluate logs at any base. So now we want to look at solving equations. For example, what happens if we want to be able to solve the equation 4 to the x power equals 17? So we're asking what power of 17 equals x? The first thing we're going to do is write that as a log. So 4 to what power is 17, or what power of 4 is 17, and that is x. Let's check. We know that this is 4 to the x is 17. That's how it's written. Good. So at this point, our x value, our answer, is whatever the log base 4 of 17 is. Well, we just need to evaluate that. I don't have a calculator that does log base 4, but I can use the change of base formula. I do know from our work that this is log base 10 of 17 over log base 10 of 4. So all I have to do is evaluate that. All right, well, so let's do that. So on the calculator, I'll actually get one of our calculators. So on our calculator here, if I do the log of 17 divided by the log of 4, I get 2.044. That sounds good. So I get 2.044 is approximately x. Okay? I can check it because I do know that that means up here 4 to the 2.044 power is approximately 17. Well, let's check that. So here in my calculator, I can do 4 raised to the 2.044 power, and notice that I get pretty close to 17. So I'm feel pretty good. Okay? All right. Let's look at another problem. We know that some of the problems that we were doing back in the exponential unit, they had an a value. So our second example, whoops, let's suppose we had 8 times 2 raised to the 3x power equals 25. So this has got an additional initial value, or a value. Before I can ask what power of 2 gives me something, I need to get rid of that. So my algebra skills say, hey, that's multiplication. I need to divide. Okay? So I need to divide that out. Over here, I'm going to be left with 2 to the 3x power. The whole 3x is in the exponent. And 25 divided by 8 is 3.125. And since that stops, doesn't go on forever, I'll write the whole thing down. Okay? Now I'm asking what power of 2, that's the same thing as saying log base 2, of 3.125 gives me this exponent, 3x. So that work that we did in Delta Math where we were rewriting is helpful here, thinking about where all the pieces go. Again, you could check it. 2 to the 3x power gives me 3.125. Yep. All right, log base 2. I can't do log base 2 in the calculator, but I can do log base 10 of 3.125 divided by log base 10 of 2. And that would give me 3x. So all I need to do then is get my calculator to evaluate that. When I get that in my calculator, I get 1.644. So that's not bad. But that's not x. I still need to finish solving. So if 3x is this, I need to divide both sides by 3 to find out what x is. And I find out that x is about 0.548. There's my answer. Well, I can check it. I can go back up top, and I can say 8 times 2 raised to the 3 times 0.548, and that should come out to be about 25. Now, as much work as I've done with exponential functions, I should know how to type that in. That should be easy. So 8 times 2 raised to the parentheses 3 times 0.548. Yep, comes out to be 25 basically. 25.002, pretty close. So I feel pretty good about that. So our answer here for x is about 0.548. All right. Well, so we've now seen a problem that had a base of 4 and a base of 2. What happens, say, for example, if our base is 10? And I bring that up because 10 is our common base that we've been working with. So let's suppose the third example is 9 times 10 to the x over 3 power equals 121. Now keep in mind, the x over 3 there is all up in the exponent. Camera likes to keep getting out of focus. So here, I need to get rid of this before I can talk about what power of 10. I'm not there yet. This is in my way. Okay, so that's an important step. So I first need to divide by 9 so that I can then get down to this part. 121 divided by 9, it's not a pretty number. I mean, it repeats, it goes on. I could write down a decimal approximation, but it's going to affect my answer. So I think instead of rounding, I'm just going to leave it as 121 over 9. I guess it's not the end of the world if you were to round here, but obviously rounding here is then going to affect the future answer. So now I'm interested in what power of 10, that's log base 10, of 121 over 9, I can type that in the calculator, is equal to x over 3. The good news is log base 10, that right there, that's log. That's what's on my calculator. So I don't need change of base formula. I just do it. I just do it. Matter of fact, so the good news is that's in the calculator. So if that's in the calculator, I'm just going to hit the buttons. Log base 10 of 121 over 9 is 1.129 about. And so then I just need to finish it off. Multiply both sides by 3. So over here I get x, and I get 3.387. Again, I could check it. I could go back and plug it in. I could say, 9 times 10 to the 3.387 over 3 power, and that should come out to be about 121. Okay? All righty. So the last thing is, what about continuous models? We did do some continuous models, some continuous compounding, or things that were growing continuously And in those cases, we had a model that often had an initial value, so maybe the initial value is 12, but the base was e. So maybe our equation looks something like this, where our base is e. Well, first thing to solving that is I can't talk about what power of e, because 12's in the way. I got to get rid of 12. So that's got to go first. So first thing happens is divide by 12. So e to the 6x is equal to, well, 138 divided by 12 is 11.5, so that's not too bad. So I can write that down. The previous problem, the 121 over 9, just like I said, didn't repeat. It repeated, but it didn't stop, and so I thought, nah, I'll just leave it. So here, I need to say what power of e of 11 gives me 11.5. So I rewrite the log again. You could check it. E to the 6x equals this. But here's what you need to know. Log base e is the same thing as natural log. And natural log is in the calculator. So I don't really need change of base formula here. You might be thinking, oh, I can't do this. I need change of base formula. You don't, because this is really the natural log of 11.5, and that I can do in the calculator. If you did the change of base formula, it would still work. You would have to use, the e in it, and that's on your calculator as well, hopefully. But the reality is all I have to do is take the natural log of 11.5. And of course, I won't be done because I'll have to divide both sides by 6. So I'll need to take whatever this answer is and divide it by 6. And so I get 0.407 when I'm done. Okay. And again, I could check it. And I've done enough evaluating with e that I should be able to handle that. But again, plugging that in, 12 times e to the 6 times 0.407 power should give me about 138. Now again, we've done enough with e that hopefully that's easy enough. 12 times e to the x, right? And interestingly enough, we can see that e to the x and ln are keys that are the same because they're inverses of each other. So that's why they're on the same key or key sequence. One's the second of each other. 6, oops, helps if you type 6, HH. 6 times 0.407. And there it is, 137.95. Yeah, I think we've got 138. I think it checks out. And so we clearly have the answer. The answer is 0.407. So basically we had 4 equations. 2 of them had base 2 or 4. And in those 2, so we had 2 to the x and 4 to the x essentially. And so those 2 we needed change of base. Let me get pulled up, sorry here. Change of base. In the other one we had 10 to the x, and so we just did log. We did log, which is log base 10. And in this third or last situation, fourth scenario, we had e to the x, and so we did log base e, which is really natural log. And so we didn't need change of base. If you use change of base on this last one, it wouldn't be the end of the world, but it's not necessary. We do need to remember, though, in all these problems, as we can see, we have to isolate or get the exponential by itself. So we have to get rid of that a value first, that initial value. And that's all it takes. At least for these, none of these were that complicated.